Try to speak.
Test. Yeah, it's working. Thank you.
Well, good morning, ladies and gentlemen. It's time to start the morning session. We'll have several talks on observational appearance and evolution of neutron stars, and we start with a presentation by Samar Safi-Harp on the observational diversity and evolution.
Is the microphone? Yeah. All right. Good morning, everyone. Thank you for being here this morning, and thank you to the organizers for the opportunity to be here today to highlight the observational diversity of neutron stars. Since we are celebrating 50 years of Pulsar's discovery, I thought I'll start with a very brief historical introduction and notes on the discovery of pulsars and on the growing observational diversity. And then I'll focus on the subclasses of neutron stars which have extreme magnetic fields, extreme in comparison to the Crab pulsar, namely magnetars, high B radio pulsars, and central compact objects, or CCOs. And then I'll highlight the growing body of evidence from observations that this distinction is blurred and that we can probably explain it even with the help of supernova remnants by magnetic field evolution. Just yesterday, we heard from Pat, or on Tuesday, we heard from Pat on how we use SNRs to address fundamental properties about neutron stars, in particular neutron star kicks and neutron star cooling. And today I'm going to focus on the topic of magnetic field evolution, including the importance of magnetic field growth. And towards the end of my talk, if time allows, I will touch very briefly on the topic of connecting the diversity of neutron stars to the diversity of core collapse supernovae, which make neutron stars. So we all know that pulsars were discovered in 1967 in the radio by Jocelyn Bell and Anthony Hewish. And a year later, the Crab pulsar and the Vela pulsar were discovered in their respective SNRs, proving Baden's-Wiki's 1934 prediction that supernovae make neutron stars. And it's thanks to radio studies as well as imaging X-ray satellites such as Einstein in the 80s and Rosat and ASCA in the 90s that we started to understand how these rotation-powered pulsars, or RPPs, power pulsar wind nebulae. And we'll hear about pulsar wind nebula later today. At the same time, there was significant growth in studying accretion-powered pulsars, which I won't address in my talk. And in the 90s, there was a surge in studying the anomalous X-ray pulsars and the soft gamma ray repeaters, which were later united under the family of magnetars, particularly thanks to the RXTE satellite. And it's worth noting that the term unusual class of X-ray pulsars was first introduced in a paper by Sandro Meraghetti. This is a picture taken at this meeting, not in 1995, saying that this is an unusual class of pulsars, unusual at the time because they have spectra very soft in comparison to the accretion-powered pulsars. At the same time, their X-ray luminosity exceeds their rotational energy loss, and therefore they cannot be powered by rotation. Now, also the term magnetar and AXP have been first coined in 1992 and 95, respectively, by these two gentlemen. And in the past decade, thanks to more radio studies and particularly the Chandra X-ray telescope, we have started to learn a lot about this growing classes of neutron stars, namely the high B radio pulsars with magnetic field exceeding the QED value and possibly behaving as magnetars, and the central compact objects, or CCOs, typified by the Cassiopeia A CCO, which are now dubbed as anti-magnetars or hidden magnetars. So we are now in the era of, instead of talking about these as different classes of neutron stars, we're attempting to unify these different classes. And I've already told you who coined the term magnetar and AXP, so I have a question for you. Do you know who coined the term CCO? Well done. So I guess I wasn't sure about that. So it was the first instance I saw was in a footnote buried in your 2000 paper, which says, according to the convention recommended by the Chandra Science Center, the Cassiopeia A CCO, which was following the first Chandra light observations of the supernova remnant, should be named CXO with the coordinates. And we use the abbreviation CCO for brevity for that particular one, and the name stuck. So he's the one to be blamed for that name. So the main question is, can we explain the apparent diversity of neutron stars by, one, their magnetic field evolution, and also by the diversity of core-collapse supernova-making neutron stars, as well as the different environments in which they evolve. And what I'm going to focus on is telling you how the hosting SNRs provide a totally independent way of answering this fundamental question. So going back to Pulsar 101 characteristics, where pulsars land on the PP dot diagram, as you know, is determined primarily by their period and period derivative, which gives us the rotational energy lossy dot. And if we have a measurement of P double dot, then we get the measurement of the breaking index N given in this formula. And under the important assumption that we have a constant magnetic field and a constant breaking index, we get this expression for the true age of the pulsar as a function of PP dot, as well as the initial spin period P0 and the breaking index. And I'll get back to this formula as I go along. So also under the important assumption that the rotational energy loss goes into magnetic dipole radiation, N equals 3, then we get these two famous formulae for the dipole, surface dipole magnetic field as a function of PP dot, and the characteristic age as a function of PP dot as well, which then lead to those lines of constant magnetic field and lines of constant spin down age on the PP dot diagram, which here shows the diversity of neutron stars, with this line illustrating the lifetime of supernova remnants, which means that objects above this line are expected to be associated with supernova remnants. So to show you the diversity, we have the rotation-powered pulsars, RPPs, with magnetic fields clustered around 10 to the 12 Gauss, like the crab, the magnetars on the top right corner with magnetic fields exceeding the QED value, and the high-beat pulsars with magnetic fields similarly high but intermediate between the RPPs and magnetars, and the CCOs, which land on the opposite end in terms of magnetic field, which are dubbed as anti-magnetars and typified by Cas A, but this is Cas 79, which has a measured period for its CCO, period and period derivative. So this is an illustration of the diversity on the PP dot diagram. Here I want to show another version. Here you have the period as a function of the surface dipole magnetic field. Battery is dying. The battery is decaying. All right, thank you. And so this is, again, showing this diversity where the magnetars and CCOs on the other side with respect to the rotation-powered pulsars. And the point here is that we can measure the magnetic field differently. Instead of using timing measurements, we can use cyclotron features as done for the accretion-powered pulsars or high-mass X-ray binaries to infer directly the magnetic field, which does not necessarily have to be the dipolar component. And that's important because it gives us insights on the magnetic field topology. So very briefly on these classes of neutron stars with extreme magnetic fields, magnetars, we heard great talks on Monday about magnetars, so I'll just skip this and just say that traditionally these are discovered as high energy X-ray and gamma ray objects, and they are not supposedly powering pulsar wind nebulae. And even though they're believed to be relatively young objects, we only have a very handful of associations with SNRs. We have about 24 of magnetars, but only about 5 associations with supernova remnants, which is a problem for studying magnetic field evolution, as I'll show you later. In terms of the CCOs, and we'll hear about CCOs more later today from De Luca. So as the name indicates, these are associated with supernova remnants. So by definition, they must be relatively young objects. They peak in the X-ray part of the electromagnetic spectrum with mostly no counterparts at other wavelengths. And very importantly, and they don't have any pulsar wind nebula around them. And the timing analysis of 3 CCOs in the 3 SNRs shown here, CAS79, PUPIS A, and PKS1209, show that PP dot imply a surface dipole magnetic field very low, between 10 to the 10 to 10 to the 11 Gauss, and that's where the name antimagnetars came from. And at the same time, interestingly, spectroscopically, this magnetic field is consistent with that determined from timing measurements, such as, for example, modeling the surface thermal emission from the Cassiopeia A CCO, as well as finding cyclotron features in the 2 CCOs in PUPIS A and PKS1209, indicating relatively low magnetic fields of the order of 10 to the 11 Gauss. These are quiet X-ray emitters, except for this very odd, interesting object CCO in the supernova remnant RCW103, which we'll hear about later today from De Luca. So moving now to blurring this diversity from observation. So I'll start with the observational evidence for this neutron star diversity being blurred. First of all, the discovery of magnetar-like behavior from 2 rotation power pulsars, which happen to be high B pulsars. These are the pulsar high B, pulsar J1846 in the very young supernova remnant CAS75, and the pulsar high B pulsar J1119 in the supernova remnant G292 minus 0.5, slightly older. And these 2 pulsars happen to fall here on the PP dot diagram close to the magnetars in terms of their magnetic fields. So these outbursts were discovered in 2006, or the outburst occurred in 2006 for this guy, and 10 years later for J1119, very recently. But these outbursts, magnetar-like outbursts, illustrated the fact that rotation-powered pulsars, these are believed to be powered by rotation, and they power pulsar wind nebulae, they can be occasionally powered by magnetic energy as well, not just rotation. Now, on the other hand, magnetars can also display properties similar to the other classes of neutron stars, namely the discovery of transient pulse radio emission from some magnetars, and excitingly, the discovery of a pulsar wind nebula or magnetar wind nebula around this magnetar, possibly associated with supernova remnant W41. And also the discovery of what's called low magnetic field magnetars. These are 3 pulsars which have a measurement of P much lower than the QED value, basically blurring the common assumption that magnetars are associated with high B pulsars, but rather can be associated with pulsars with a dipolar field very similar to traditional radio pulsars. So that was highlights from the observational evidence of the diversity being blurred. Now moving to some theoretical work that attempts to unify the subclasses of neutron stars. And this is a plot resulting from great work by Vicano et al., which attempts to unify the different subclasses here, magnetars, the X-ray dim isolated neutron stars, which we'll hear about later today, high B radio pulsars, and rotation-powered pulsars, using a magnetothermal evolution model. So what you're seeing here on the PP dot diagram, curves that correspond to different values of the magnetic field ranging from 3 times 10 to the 12 to about 10 to the 15 Gauss. And these lines, these dashed lines are lines of constant magnetic field, but these lines take into account the evolution of both the temperature as well as magnetic field decay. So this study shows the importance of coupling the temperature and magnetic field evolution, and particularly the Hall effect for magnetars, in order to unify these subclasses. Now, what I'm going to describe next is what I said I'll focus on, is that supernova remnants can provide an independent means to address magnetic field evolution. And the work I'm going to show next is done in collaboration with my postdoc, Adam Rogers, who's shown here. So to perform the study, we collected a sample of pulsar SNR associations, again focusing on those extreme magnetic field subclasses, magnetars, AXPs, and SGRs, high B pulsars, and CCOs. And to that, we added 2 rotation-powered pulsars with measured breaking, low breaking indices. And we do that because we wanted to compare to a study done by Win Ho, who considered magnetic field growth in young rotation-powered pulsars. But for this sample, it's a very small sample, really limited. But that's because we decided to focus on just the secure associations and those that have a measured supernova remnant age, because we want to use this age as a constraint as the true pulsar age. And so these are the properties of the pulsars, these are the associated SNRs, and these are the ranges of the SNR ages. And all these properties are compiled and try our best to keep them up to date in the high energy catalog of supernova remnant developed at the University of Manitoba. So one thing to note is the huge age discrepancy, as you all know, in CCOs between the characteristic ages of pulsars and their much younger supernova remnants. Another interesting one is the anomalous X-ray pulsar 2259 in the supernova remnant CTB 109, where also the characteristic age is way higher, orders of magnitude higher. So you remember this formula that I showed at the beginning of my talk, which makes the assumption that the magnetic field and N are constant. Now, what I'm going to do here, I reordered this expression, where here we have the initial spin period expressed as a function of PP dot, which are measured, the age, the true age of the pulsar, and the breaking index. And here we're going to use these SNR associations to constrain the age for the pulsar. And if we do that, then we can plot P0 over P as a function of the breaking index and look for the allowed values that are constrained by this SNR age. And these are shown in these gray shaded areas. So the first thing to note is that P0 over P is actually not necessarily much smaller than 1. These are two AXPs and 2 SGRs associated with supernova remnants. And this is contrary to the common assumption that P0 has to be much smaller than P, especially for the magnetar model. The other observation to make is that for these 2 high B pulsars, in some cases we have a measurement of the breaking index, which is an additional constraint. And in this case, at least, and another case that Pat showed on Tuesday for G292, for example, the breaking index required by constraining the age of the pulsar by its associated SNR is not consistent with the one measured. So there's a problem there. In other words, we are unable to explain the observed breaking index and enforce the ages to be equal with a constant N, implying the need for a time-dependent magnetic field, which is expressed here. This is the equatorial field as a function of time, with this function which takes into account the time evolution. And if you assume a time-dependent magnetic field, then the breaking index will have this expression with F dot here. And for N to be smaller than 3, we have seen that the measured breaking indices for many pulsars are smaller than 3. If N is smaller than 3, then F dot has to be positive, which means that the function F, the field is growing. Now, moving to the subject of magnetic field growth, this is not a very new idea. In fact, it started being investigated shortly after the discovery of neutron stars, including work done by Zeldovich, who's shown here. I took a picture of him here in the hallway. And the submergence of magnetic field due to fallback accretion has been investigated by a number of authors in the 90s. And it's just recently revived due to a number of observational facts by a number of authors. Some of them have given talks here at this conference, including our chair here of this session. So this magnetic field growth has been revived because N, like I mentioned, is smaller than 3. we know that the magnetic field is very small from both timing as well as spectroscopic measurement. And in the case of Cas79, the presence of a highly modulated pulse signal implies that there must be a much higher internal magnetic field, suggesting that these are born with high internal magnetic field. And if there's fallback accretion, it takes time for that to emerge to the surface. And so this is how we describe the submergence of the magnetic field with time. And so using that sample of pulsar SNR associations that I showed you, that very limited sample that we focus on, we developed empirical parametric models for describing their evolution based on previously developed models by a number of authors. And this is an attempt to unify the magnetic field growth and decay. This is the expression for the magnetic field decay, which is based on models developed by Colpi and elaborated on by Daloso and applied by Nakano to explain the age discrepancy for the anomalous X-ray pulsar 1E2259 in CTB 109. So Magneto or AXPs at least require magnetic field decay for these time scales. Now, based on that parametric expression, we developed a parametric model for magnetic field growth, which actually takes into account also previous work done on magnetic field which are buried under the crust. And we explored the flexibility of this model, which is parameterized similarly to the decay models, by trying to reproduce the results obtained from previous work on buried magnetic field in young neutron stars, particularly using a magnetic field decay by these authors, and also reproducing the results of Win Ho, who studied magnetic field growth in both young rotation pulsars with low breaking indices as well as CCOs. And these are the solutions to the field evolution in that sample, very limited sample. I describe what you're seeing here is the characteristic age of the pulsar as a function of the age of the SNR. And this gray area describes the joint fit to the anomalous X-ray pulsars using the magnetic field decay. The blue curves correspond to solutions for the 3 CCOs using magnetic field growth. And the late time evolution of this characteristic age in the case of the 3 CCOs actually explains the huge age discrepancy with their associated SNRs. In particular, if you see these lines intersect the line where the pulsar equals to the SNR ages at times that exceed 10 to the 4.5 years or so, which means by that time the supernova remnants would have dissipated. In other words, the characteristic ages for these pulsars considered will never reflect the true ages as long as they're inside their supernova remnants. Now, showing these same evolutionary models on the PP dot diagram, and I'm focusing again here on those blue curves, which describe magnetic field growth. So the assumption here is that the magnetic field will emerge on a certain time scale, and then it will reach this asymptotic value. This asymptotic value varies between the models or the CCOs considered. But however, this suggests that CCOs can be ancestors of other older classes. If the magnetic field lands on the high magnetic field value, they could be ancestors of the X-ray dim isolated neutron stars. But if they land on the lower end, they could be ancestors of the older population of radio pulsars, as long as they survive the accretion phase, which should be X-ray dominated phase, and the magnetic field that emerges is high enough for radio emission to occur. So in summary, what I told you is that our model, even though it's just a parametric, simplistic model, supports the idea that these apparently different classes of neutron stars are actually united through magnetic field evolution. So moving to the second and much briefer part of my talk is about connecting the diversity of neutron stars to the diversity of core collapse explosions. And we heard about supernovae, explosion mechanisms, and supernova remnants in talks on Tuesday. There are some interesting questions to address. What I'm showing here is the old historical classification of supernovae based on their optical spectra. And we're interested here in core collapse supernovae, which are shown here with the different subtypes, eventually implying different progenitor masses, with progenitor masses going higher to the left in this case. And some questions I'm particularly interested in is which types of supernovae make magnetars and even CCOs? And the fundamental question, what type of explosion made the Crab Nebula? How much time do I have? 5. So I'm going to just skip the part on magnetars and high B pulsars because I want to show you something interesting from Hitomi on studying the Crab Nebula. So I started with the Crab, and I'm going to end with the Crab. The Crab is our poster child for a core collapse explosion. Despite that, we still do not understand the explosion. When viewed as a supernova remnant, it has an uncomfortably very low mass, ejecta mass of about 4.5 solar masses, and very low kinetic energy of about less than 10 to the 50 ergs. Moreover, the shell, the supernova remnant shell expected from this explosion is still missing. Despite deep searches for that shell, in radio and in X-rays, none was found. Where is it? We call them the shell-less supernova remnants, and there's about 24 of these in our galaxy. So 2 scenarios have been proposed in the literature. First, we have a typical iron core collapse 10 to the 51 ergs explosion, and the only thing is the shell is there. It's just way beyond the Pulsar wind nebula, and it must be carrying a lot of the mass and the kinetic energy. But like I said, despite deep searches for that shell, it's still not there. And the other interesting scenario, which was proposed in the 80s by Nomoto et al., is that this is an anomalous explosion to start with. I mean, we're starting to believe that the Crab is anomalous anyways to start with. And that explosion in this case is low energy, 10 to the 50 ergs, resulting here in an electron capture supernova, as opposed to the typical assumed iron core collapse explosion. So what did we do with Hitomi to address this important question? As you know, Hitomi is a Japanese-led X-ray mission. And this mission had 3 detectors on it, spanning a wide X-ray band. But the most important one was the microcalorimeter, or the soft X-ray spectrometer, which has an unprecedented sensitivity, a spectral resolution of about 5 electron volt, and sensitivity to thermal X-rays. And this mission was successfully launched in February 2016, thus the smiley face. However, 6 weeks later, the mission ended, unfortunately. During 6 weeks later. Oh, sorry, yeah, that should be 2016. That's a wishful thinking. During those 6 weeks, very brief time, there were a number of observations performed of the Perseus cluster, amazing results done there. And there were 3 observations performed, very brief observations, I would say snapshots, which are part of the calibration program. And that includes the Crab just before the end of the mission life. The observation was very brief. Here, I just want to acknowledge the contributions to the Hitomi mission. Here, I'm just showing a picture of the partial team shown here. But the spectrum shown here with the soft X-ray spectrometer, or the microcalorimeter, unfortunately was only from 2 to 12 keV. That is, we were missing the soft X-ray band, which was the interesting band, because the gate valve was closed. And that was because we were early in the phase of the mission. So we didn't have any counts below 2 keV, but this is the spectrum in just 10 kiloseconds, more than 550,000 counts. And the observation was pointing towards the center of the nebula, unfortunately or fortunately, depending what you're interested in. So there was, unfortunately, no evidence of any line emission in the spectrum, despite searching using different methods. But a new upper limit, a very stringent upper limit on the X-ray emitting mass has been obtained of about 1 solar mass. That was obtained actually making use also of previous Chandra observations dedicated to look for that thermal X-ray emission. And that was done for a wide range of assumed shell radii and plasma temperature and ionization timescales. So no thermal X-ray emission, but we have a new upper limit or a stringent upper limit on the X-ray emitting mass. So going back to our 2 scenarios that I mentioned, in terms of explaining the explosion mechanism, we explored the parameter space for these explosions using hydrodynamical simulations developed by Lee et al. And these 2 explosion mechanisms, I remind you, are the iron core collapse 10 to the 51 ergs versus the electron capture 10 to the 50 ergs here on the right side. And we explored 2 different environments, the interstellar medium uniform ISM to the top and a progenitor wind to the bottom. And the bottom line is that even though the electron captured low energy explosion has been favored by a number of studies, this result does not rule out yet an iron core collapse 10 to the 51 ergs energy explosion, as long as we believe an extremely low density for the interstellar medium, less than 0.03 particles per cubic centimeter, which is lower than in the case of the electron capture. And the only way to distinguish between these 2 models is really to have pointings away from that nebula, so we can distinguish between the 2 because they have different predictions. And that was going to happen next, but the mission ended. So to summarize, we have gone a long way since the discovery of the Crab and Vela pulsars, now 50 years ago. The diversity is blurred with growing observational and theoretical work. And the unification is getting closer and closer when we consider magnetic field evolution, in particular, magnetic field growth for the younger population of neutron stars, in particular CCOs. The magnetic field topology is also very important. I didn't have time to talk about this, but this was covered in a number of talks at this meeting. But one thing I should note is that the toroidal component of the magnetic field is extremely important. It has been shown both theoretically and observationally that it can explain the diversity of neutron stars. In particular, theoretical work done here stresses the importance of a toroidal field in explaining magnetar-like behavior from low magnetic field pulsars, as well as the anti-correlation between magnetar outbursts and the age of the system. And observations, whether from cyclotron features, indicate the presence of very strong toroidal components either on the surface of neutron stars or inside the neutron star. Moving on to future prospects. So the loss of the Hitomi mission was a huge blow for X-ray astronomy. However, we have a number of missions recently launched or about to be launched. Rosita, we'll hear about that later this session. But this is going to be very important because it's going to help us expand that extremely limited sample of pulsar SNR associations. And on top of that, hopefully it will allow us to discover X-rays, softer X-rays or weaker X-rays from the CCO descendants. And that's going to be very important to address magnetic field evolution. Timing measurements, very important still. We have a very limited sample for breaking index measurements. We're still missing breaking indices for these interesting classes of neutron stars. It might be a hopeless thing, but if the dipole indeed emerges to the surface, there might be some signature there that we can detect with a breaking index. And RxTE is gone. We have SWIFT. But also, India launched AstroSat 2 years ago. And just this past month, NASA launched NICER, the Neutron Star Interior Composition Explorer. And China launched the hard X-ray modulation telescopes, which can address some of this science. And last but not least, high-resolution X-ray spectroscopy, which we tasted with a very brief phase of Hitomi. This is going to be important because, one, for this particular science, it will allow a direct measurement of the magnetic field, not just the dipolar component from cyclotron features, as well as in terms of the SNR associations, it will allow us, one, to refine the ages, and 2, to constrain the progenitors of these objects from accurate abundance measurements and comparing them to nucleosynthesis models, and then address the diversity of neutron stars to the diversity of supernovae, core-collapsed supernovae. So now NASA and JAXA are committed to launching a recovery mission, the X-ray Astronomy Recovery Mission, also referred to as CHARM, Astro H2, by 2021, followed by ESA's Athena, and hopefully NASA's Lynx in 2028 and beyond. So, so the future is bright, and let's hope for another 50 years of great neutron star science. But for people like myself, I just hope to make it to 2054, because that's the 1000th anniversary of the supernova 1054. And while on the topic of celebrations, I learned this week that Dick Manchester, is Dick here? Nope. Just celebrated a big birthday. And when I looked at ADS, I noticed that his publications go back to 50 years ago. So I thought we'll use this as an opportunity to wish him a happy birthday and thank him for all his great contributions to pulsar astronomy, literally the past 50 years. In particular, this pulsar catalog, which is a great service to the pulsar community. Thank you very much.
Thank you. And we have time for a couple of questions. Sergey.
About Crab supernova,
yeah.
In addition to remnants, one can look into historical light curves, and we tried to do this with Nozomu Tominaga and the same Ken Nomoto in APJ recently, and there is no hope to have standard 10 to 51 Hz. Just very low energy is okay. Another short historical comment: the diversity of remnants was suggested again by Shklovsky to study the diversity of explosions in different galaxies. In this way, he predicted 87A. It would be blue supergiant.
Right. Thank you for pointing that out. And I didn't get the chance to talk about the observational evidence for supporting the low energy explosion for the crab, but yeah, the abundances is one of them, and historical light curves.
How can you plan to make the direct measurements of magnetic fields? What do you mean?
Which measurements? Sorry, can you repeat the question?
You plan to make direct measurements of magnetic fields.
Direct measurements of magnetic fields. I mean, not just me, a lot of observers do. So it's actually based on, again, that's why I showed this one. So it's really based on cyclotron features, which have been used as a way to infer directly the magnetic field. So that was a method used for high-mass X-ray binaries. And in the case of the isolated neutron stars, there is evidence for cyclotron features where one of the interpretation, and a lot of this work was done by George and collaborators, is that there is evidence of cyclotron lines that imply a magnetic field of a certain value. For the low magnetic fields, this falls in the X-ray regime, and if it's a proton cyclotron line, it would indicate a magnetar strength, or 10 to the 14 to 10 to the 15 Gauss magnetic field. So the quick answer is cyclotron features.
These lines are protons in the cyclotron lines.
No, I mean, we make an assumption, but yeah.
Okay, I think we'll move it to the coffee break, and please, the final question.
Thanks, Sama. Nice talk, especially the last bit. Yeah, I have a question though. How do you rule out the possibility that these CCOs were born with long periods to explain the characteristic age discrepancy?
How can we rule out that CCOs are born with long periods? I mean, it's certainly a possibility that they are born with long periods. I guess the question is whether they're born more with higher or lower magnetic fields. So I was focusing on the fact that the magnetic field, they can be born with a high magnetic field, but it's very deep interior, and then it emerges on a certain time scale. But the initial period has to be close to the current period. Does that answer your question?
Well,
are you looking for observational evidence for that, or
I
tests?
think it's a possibility you can't rule out. So I don't. It seems to me it's not necessary to invoke field growth. Even the breaking indices less than 3 can be explained if the breaking is due to a stellar wind.
Oh yeah, sorry,
particle wind.
I did not discuss that, and we do discuss it in our paper, but I totally agree that in this very, where is it? See that faint note, relativistic winds imply n smaller than 3. So for the ones that have pulsar wind nebula in particular, relativistic winds should be considered, and they can explain. So actually follow-up work on the sample that we did that I didn't even discuss is trying to constrain the luminosities using the luminosities of these objects that have pulsar wind nebula and a measured breaking index in terms of the contribution of the relativistic wind to this. So yeah, that's definitely very important. But in the case of the objects like CCOs and magnetars in general, we don't see pulsar wind nebula around them. So the effect of the wind, relativistic wind, is not that important there. As for the rotation-powered pulsars, for example, and the high B pulsars.
Okay, we have to move on. Thank you once again.
Thank you.
We continue with the second presentation by George Pavlov.
Good morning. So I will be talking about ultraviolet emission from isolated neutron stars. Basically, this all are Hubble Space Telescope observations. And here are my co-authors. So it's contents of the talk. I had a temptation to put it in historical sequence, but it would be too difficult. So different topics are here ordered with age, from very young pulsars to recycled pulsars. I would say the most recent and therefore interesting results are among these two topics, so I will try to reach them by the end. And here is a short introduction. Talking about ultraviolet, I will be mostly talking about these two bands. In terms of wavelengths, it is between 2,000 and 3,000 angstrom. It's near UV, and below 2,000, it is far UV. And so, crudely speaking, it is between 4 and, say, 11 electron volts, because energy is close to the Lyman break, to the photoionization potential. Is hard to observe. Why it is important for studies of neutron stars? I think the main, mostly important thing that observing in UV, we can detect thermal emission from so-called neutron stars, old neutron stars, that they are undetectable in X-rays. And also we can investigate Rayleigh genes, that slow frequency tails of thermal emission from hotter middle-age pulsars. And this is interesting, and of course all this requires space telescope. Just 2 words about what I mean isolated neutron stars. Neutron stars can be in binaries, but the companion should make no effect on the neutron star itself. So mostly there should be at least no accretion. Samar explained us that there are these main 4 classes of neutron stars. We can observe thermal UV emission only from these 2 because of different reasons. Yeah, regarding central compact objects, I possibly should apologize for introducing so weird notation. The reason of that was that it was introduced when we studied Casey, first Chandra data, and at that moment it was not clear that it is a neutron star. There were speculations that it might be an accreting black hole or maybe a strange star, meaning made of strange quarks and so on. So we, I chose this neutral, uncertain term, central compact objects. So for me personally, beginning of this story of UV observation started in 1987 when there was a first call for proposals for space telescope. And at that time, I figured out that nearby neutron stars, nearby pulsars can be detected, thermal emission from nearby stars can be detected relatively easy, and we submitted a proposal. The proposal was accepted, and these 3 pulsars, which at least people from radio pulsar community know very well, were proposed for observations. We were very happy about that, but unfortunately the program was cancelled because of this infamous HST aberration problem. So we proposed again in 1992. 2 of these pulsars are the same, and we added this middle-age pulsar, which was detected by that time in X-rays. We proposed, of course, observations in several filters. The telescope allocation committee said, no, several filters is too much, you at least should detect it. So these were just observations with 1 filter, which is not interested. And finally, the observations were carried out. The result was still interesting, although somewhat uncertain. And I would say that this range of 7 years, from 87 to 94, is kind of a typical range after you suggest to observe something and get the data and publish something. So I very quickly will try to go through different ages of neutron stars, what we see from them. The very first neutron star observed in UV was, of course, the famous Crab pulsar. It was observed with high-speed photometer in near UV, and later was observed with space telescope imaging spectrometer in NUV and FUV. And the spectrum, observed spectrum, is shown here. At first glance, it looks puzzling and strange. What is that? But in fact, it's not. It is not so interesting, because if you make a correction for the interstellar extinction, you will see that even if you include optical frequencies, here are wavelengths about 8,000 angstrom. From the optical, even near infrared, till far UV frequencies, it is well fitted by a power law. The slope is somewhat uncertain, but it is close to 0. Uncertain in a sense that it depends on the color index, on the amount of extinction. What is important is that the slope is the same in the ultraviolet and optical. So most likely it is a magnetospheric, most likely synchrotron emission. Also, in those observations, pulses were detected. What is shown here, but can be hardly seen from a big distance, are pulsations in far UV solid line and near UV dashed line, and they virtually coincide, and actually they also coincide with the optical. So in this respect, crab is not extremely interesting. We just proved that it is the same emission in a very broad range. Next, young pulsar, but much older, is the Vela pulsar, which was observed by our group in 2002. We got a spectrum in far UV and imaging in near UV. So what was the result? Again, it was a timing observation. It showed at least 4 peaks per period, which is very unusual, but Vela pulsar is also a peculiar pulsar in that respect. And in terms of spectra, we saw that at different phases, we have somewhat different slopes of the spectrum. But on average, it was close to 0. In principle, we were going to detect thermal component, but it was not deep enough observation to really obtain it, so the spectrum is shown here. So we got some upper limit on the brightness temperature. Now about middle-age pulsars. I will start from Geminga, which is most famous of them. First observation of this pulsar was done with faint object spectrometer in 2 optical and 1 in UV filters. So these are optical and this is in UV. What is shown here is F nu versus nu in log scale. So what we see, or what the authors see here, is it looks like several points lie along the Rayleigh-Jeans line, Rayleigh-Jeans spectrum, if nu proportional to nu squared. But these points do not lie there, so there was some enthusiasm for a while that it might be a spectral feature, proton cyclone emission, and so on. Later it became clear that no, it was not like that. We observed it in far UV in 2002, and also with NUV in the same program. So what is shown here is F lambda versus lambda. And these points, or say this line, correspond to lambda in the power minus 4, which is again a Rayleigh-Jeans spectrum, so it is a thermal emission. And if you look at the whole spectrum, adding optical points and near-infrared points, you see this, what we now understand, more or less typical spectrum for a middle-age pulsar. Sorry, again, it is F nu versus nu, not like in this picture. So what we have here is a combination of a power law spectrum and the Rayleigh-Jeans spectrum. And from the Rayleigh-Jeans spectrum, we can estimate the temperature, which in this case is written here. And we can measure the slope of this spectrum. In the same observations, we detected pulsations, and here is sound NUV and FUV pulsations, which look strange. What is particularly strange is this very narrow dip in the light curve, because the emission is thermal, and we should not expect any sharp features there. And it is still unclear what is the reason for that. If you look at the spectrum as a broadband spectrum, so again, what is here is F nu versus nu, and these are X-rays, and this is optical, and this is far UV. So in X-ray, we do see thermal emission. We see 2 components, hot and cold component. And if you extrapolate the cold component, it is close to the Rayleigh-Jeans, which we detected in FUV. If you extrapolate the power law component, it goes like this. Most likely it doesn't match the optical spectrum, which means that there is a spectral turnover at these frequencies. Now the next, now quite famous pulsar is 0656. It is a middle-age pulsar. First observation was our first program in 1994. So it was just observation in one filter, and you got just 1 point and nothing else. But by that time, there were some X-ray data and crude extrapolations from X-ray to UV and optical. It goes like this. So we just speculated that likely there should be, again, a non-thermal emission and a Rayleigh-Jeans tail. Later, we did more observations and obtained more points, and that prediction sort of was shown that it was correct. So again, it is a combination of a thermal spectrum, which decreases pretty fast with frequency, non-thermal spectrum and Rayleigh-Jeans. Even more observations with HST of that pulsar, it showed some somewhat strange things, or maybe not strange. So these are observations with grating and with cosmic origin spectrograph, again with grating. So this is absolutely certain that it is a thermal emission, it is a Rayleigh-Jeans. Here are some new infrared points, but measurements with relatively narrow filters, so-called RAM filters in the optical. They showed somewhat strange spectrum, apparently with spectral features. Are they real or not? We're still not sure, but it would be good to investigate. It is interesting to compare, say now, Vela, Geminga 0656 and Vela, to compare the spectra from near-infrared to FUV. So this is Geminga. This is 0656. They're pretty similar. And this is Vela. It goes like that. It goes like that. Also, it is interesting, but for sure I have no time for a detailed description of what we see here. This comparison of pulsations. So these are three pulsars, and these are different ranges. So near UV, far UV, soft X-ray, harder X-rays. If you just look at this NUV and FUV, we see how different are the light curves, the pulses in the Vela and in these middle-age pulsars. Also, it is interesting to compare X-ray to optical behavior. So this is Geminga 0656, Vela. So what we see here is that optical extrapolation of the thermal emission more or less coincides with the Rayleigh-Jeans tail for these two pulsars. But what we see is that in Geminga and even more clearly in Vela, clearly there is a spectral turnover of the non-thermal spectrum. In the last middle-age pulsar is 1055 minus 52. It is also a well-known pulsar. This is the only image which I show just to demonstrate one more advantage of FUV. This is the same field. This is an F star, and this is how it looks in the some red filter, which is written here, and here how it looks in FUV. So this is a star, this is a pulsar, and this is the same star and the same pulsar. Here the pulsar is too close to the star, very close to the star, so it is difficult to measure its properties. Here it looks well separated. Now what we see for this pulsar, this is optical UV spectrum, it's optical points, and this is FUV point. And from this, again, apparently we see a Rayleigh-Jeans tail and non-thermal emission, but there are actually too few points. Now if you compare, if you add X-rays here, this is thermal X-ray, this is non-thermal X-ray. What is most striking in this picture is a mismatch between the extrapolations from the X-ray to optical, and the reason for this is not fully clear. And in this picture, simply gamma emission is added. It looks like there is some strange behavior with hard X-rays in gamma rays, but it's not that important to understand what is going on. Of course, it is obvious that we should observe here, and we should to take a real spectrum here. 7 proposals to do this were rejected. It's not an unusual situation. Now, thermally emitting neutron stars, the most famous of this is this RxJ 1856. It was observed first time in 2000 with a spectrometer. What is shown here is of lambda versus lambda, and this is the observed spectrum, and it is consistent again with Rayleigh jeans. And if you add optical points like here, it is even more consistent with purely thermal spectrum, no non-thermal component. What is also we see in this picture is a so-called optical excess. This curve is extrapolation from X-rays, and this is what we observe. So what we observe is brighter than, it is brighter than what we could expect. And no pulsations were seen. This is the next star of the same family. These are different points. Again, we see optical excess, and we see some hint of some difference between the pure Rayleigh jeans, which would go like this, but it is not clear. Yeah, of course, in all these cases, we can estimate at least brightness temperatures. Then there was a very, very nice program proposed by David Kaplan and Martin van Kerkwijk to observe the rest of this magnificent 7 in just 2 points. 1 point with 2 filters. One filter would be for UV, and the other filter would be optical. And what will we see? And actually what was seen is kind of in disagreement with the generally accepted paradigm, because it was assumed that all the sources should be like this. We have something in X-rays, again it is of lambda versus lambda. We have thermal emission in X-rays, and we have this observation in the optical, and this is a Rayleigh jeans tail, and it is parallel to this and some optical excess. However, in several cases, quite different slopes were seen. And it means that, no, it is not a purely thermal emission, there is something else. What else, it is still unclear, but it is very strange thing. This picture actually shows the same thing. So in this picture for 5 stars, what is shown in this, is it cyan, the color? It is a measured spectrum, it is X-ray extrapolation, and we see that for this specific object, which I guess is 1856, they are parallel, but in this case, they are not parallel, and optical excess here is a factor of 50, which is also very, very strange, very strange. All attempts to understand what is in between, what is that, they were unsuccessful. Attempts, I mean proposals, were unsuccessful. Now, more recent things. So, old ordinary pulsars. The first one, it is 0950, which was first time observed with just 1 filter, and this is a flux, and this is a wild speculation if it is a thermal emission. After that, there were several optical observations with Subaru and VLT, in which our colleagues Yuri Shibanov and others participated. And this point, they clearly show, first of all, they show scatter because there is some background galaxy. And they show that this emission is not purely thermal for sure. So finally, 2 years ago, our proposal obtained some time to observe it in FUV. And here is the result. Here is the result. So these are optical points. This is our first observation 20 years ago. Not 20, 25, something like that. And this is a FUV point. And we clearly see that in this picture, for sure, this is thermal emission. One could say, okay, what's interesting at this thermal emission? We see the same thing in middle-age pulsars, but this thermal emission corresponds to the temperature, say, crudely speaking, 10 to the 5th Kelvin. It means that this pulsar, which is 17 mega years old, is pretty hot. And it certainly proves that there is some heating mechanism. What is this mechanism? We, of course, do not know, and there are different possibilities. But again, what is bad, or say to measure this temperature more accurately, we should have more observations, more HST observations, which would give us much better data, but the proposal was again rejected. We also observed, also quite recently, a very old, the oldest, slowest, closest ordinary pulsar, and we did not detect it. And we put a temperature limit which is quite low, for 10 to the 4th kelvins, which is a record low upper limit. So at least very old pulsar indeed cold. Now the last topic is millisecond pulsars. The most famous, again, millisecond pulse, the closest, okay, millisecond pulsar, a distance measured with an accuracy of 1/10 of a parsec, is this one. And we observed it with STIS far UV grating, and we got these points. Now, this pulsar is not a single pulsar, not a solitary pulsar. It is in a binary with a white dwarf. And there were plenty of optical observations, and here are the points. And what we actually see in this picture is the white dwarf spectrum and pulsar spectrum. And apparently, this pulsar spectrum is again a Rayleigh jeans. It is thermal. And the brightness temperature, very crudely, is like this. And it is also not expected by everybody that a giga years old pulsar is so hot. Then we had more observations, and we got much more points, and we also observed it with Spitzer and in infrared, and we got this nice spectrum of the pulsar, white dwarf. This is thermal component, and here is actually very small contribution of the non-thermal component, which is almost not seen. And we measured the temperature more accurately, and it is written here. And there are different speculations, what could it be, including some hardly plausible, but exotic ones at least. Also, observing this pulsar, we accidentally discovered something which completely was not expected. It is far UV Bow shock, which positionally coincided with H-alpha Bow shock. H-alpha Bow shock was discovered long ago, in 1993, if I remember right. So this is a pulsar, this is a Bow shock, and this is some image from ground-based observations. And what we see in FUV is shown here. Here is a pulsar, and here is a Bow shock. Here is, I don't see, here is a pulsar, here is a Bow shock. This stuff is artificial, it is instrumental effect. What is also interesting, if you estimate the luminosity in the FUV bow shock, it is crudely 1 order of magnitude higher than the luminosity in H alpha. What exactly is the nature is still not clear. It could be simply emission of plasma heated by passage through the forward shock interaction with the pulsar wind, or it could be something more unusual like synchrotron emission from relativistic pulsar wind electrons, which are somehow caught here. I will not discuss this at all, and instead say a few words about another millisecond pulsar. This time it is solitary pulsar, no white dwarf and other garbage, and so we observed it again with this FUV filter, and with this broad optical filter, and we got the following. We got 1 point here and 1 point here. This point in terms of flux is at reasonable assumptions of the extinction. It is somewhat above this point. In principle, they could be fitted by one power law spectrum, and then it would be a spectrum similar to the crab, which may look strange but cannot be firmly ruled out. If you take a typical slope of the non-thermal emission, just assume it's about -1, then we will have to say that this is again a thermal emission, and again its temperature is about 10 to the 5th Kelvin. So it is a second millisecond pulsar with this big temperature. So from observations of these 2 millisecond pulsars, we can conclude that most likely heating is required. And finally, for this pulsar, we again see the bow shock in the far UV, which is shown here. Here is the pulsar in the circle. It moves in this direction, and this is the bow shock. What is interesting and somewhat strange, that no bow shock is seen in the optical, although that optical observations is much more sensitive. So maybe indeed it is somehow concentrated in the far UV. It is still not clear. Well, it is, of course, would be useful to study this phenomenon. So I'm about summary. So 26 years, 17 neutron stars observed, 16 detected, and the non-detection is also interesting in this case. So about very young pulsars, ultraviolet spectra magnetospheric, slope varies with pulsation phase. Middle-aged pulsars, we see thermal Rayleigh-Jeans tails. We observe some mismatches between optical and X-rays. The reason is still unclear. We see some puzzling pulsations. The reason is not fully clear. And it is clear that non-thermal emission, optical emission is virtually always non-thermal. Now the thermally emitting isolated neutron stars, it's mostly thermal UV spectra, but in some cases there are strong deviations from thermal. Old ordinary pulsars are hotter than expected if we assume a passive cooling, but only 2 observed. And of course it may look strange that in 26 years we were not able to see more. The sources, and finally millisecond pulsars, only 2 were observed. Both are hot, and both show far UV bow shock. We know that HST will likely retire soon, and no other space observatories will be available for UV observations, and that means that we should use the unique UV capabilities of the HST now. And therefore, please take this into account if you are the members of Telescope Allocation Committee. Thank you.
We have time for written questions.
You quoted a number of temperatures of this. Just in two cases, it was specified that they were brightness temperatures. What are the other cases? Are there black body or atmosphere?
No, these are always, excuse me,
because you know the difference may reach a factor of 2 or 3.
I know this, yeah.
Yes, of course.
Okay, it's not a place for discussion. Atmospheres are not related to this at all.
I would like to say that Geminga is not a radio-quiet pulsar. It has been detected at low frequencies by the Pushkin group. It has very variable, but well-registered pulses. These results are published 2 years ago in astronomy reports.
Yeah, I'm sorry. I know about this result. I know about some similar result claimed by Indians recently. So it was kind of by inertia. But anyway, it is weak. It is seen only at very low frequencies. And if, as far as I remember, there were still some puzzling and suspicious things. I'm not saying that's the wrong result, but it is not really important for this subject.
A question and a comment. The question is, these pulsars with a requirement for heating, extra heating, do you have a plot of their detected thermal luminosities versus their spin down rates or rotational energy loss rates? Is there a correlation still?
Not for these pulsars. I wanted to make this plot for this talk, but I failed to do that.
And the comment is about the recent work by Ünal Ertan and others for the optical excess in the Magnificent Seven. He finds that if there is a fallback disk around them with a propeller mechanism, the coupling with the neutron star, the mechanical work done, dissipated in a boundary inside, matches the optical excess.
Yeah, I remember about that paper. It looks like a plausible explanation. But one can say, why do we see such things only around these strange objects? Well, not strange, but around these 7 objects, and we do not see them in other pulsars.
No, that model says we do see, or we do expect these fallback disks to be present on around a number of different kinds of sources, not just those.
Okay, thank you.
Thank you. No, unfortunately, we don't have time, and we have to move for the third talk by Adriana Pires, again on isolated neutron stars, and hopefully future observations with the Rosita.
Okay. Hello, everyone. It's a pleasure for me to be here today. I'm Adriana Pires from the Leibniz Institute for Astrophysics, Potsdam, and I'm here to talk about our expectations for the population of thermally emitting neutron stars to be detected by the Rosita survey. I would like to acknowledge the work of my collaborators, as well as the Rosita German Consortium. So the neutron stars we observe are dominated by pulsating sources of radio pulsars. And 50 years after the discovery of the first pulsar, over 2,600 objects are now known, and these mostly come from radio pulsar surveys. They are divided into two main groups, as we know. The canonical neutron stars, rotation-powered pulsars, and the millisecond fast-spinning pulsars, which are thought to be recycled in binary systems. There's also a growing number of radio transits called RATs that are being detected by dedicated searches in radio pulsar survey data. And only about 2% of the observed population consists of peculiar groups of X-ray emitting stars, which I will concentrate on my talk here. So thanks for the very, very good overview given today by Samar's talk, and also other people in this conference. I don't need to spend much time to talk about the phenomenology of these different groups of neutron stars, in particular the X-ray emitting neutron stars, magnetars, the group of nearby cooling neutron stars discovered by Rosat, which I call here Magnificent 7, and CCOs. It's only important for me now to stress that these objects completely escape radio and gamma ray pulsar surveys. And yet they do, their properties challenge our understanding of neutron star emissivity and evolution. So the question is, do radio pulsars tell the whole story? Let's have a look again at the PP dot diagram of isolate neutron stars. So a standard picture of pulsar evolution tells us that neutron stars are born rotating very fast, and they will evolve along lines of constant field towards longer periods until the pulsar is not energetic enough to create pairs of positron electrons that are responsible for the radio emission. So until a certain point, the pulsar is not detected in the radio wavelengths anymore. And this is what more or less radio pulsars tell us in a broad sense. Now, when we add the peculiar source to this diagram, we see there's something that starts to not fit completely on this simplistic scenario. First of all, magnetars are up there, where very highly magnetized neutron stars should be. The Magnificent 7 are located more or less intermediate between magnetars and the bulk of the population. And indeed, the Magnificent 7 do show, in a smaller scale, properties that are similar to magnetars, in the sense that they have also brighter thermal emission and also long spin periods. And finally, CCOs, the three CCOs which we know, P and P dot, are in this part of the diagram, which is important to notice that is very sparsely populated. So the question is, if there is no field evolution of these objects, we should see evolved CCOs, old CCOs in this part of the diagram. And we don't. Radio surveys and X-ray surveys, people were trying to see their descendants around this area of the diagram, and we don't see them. So again, that's something that goes against the standard picture. Now, to understand that, let's have a look at how fast a neutron star cools down. This again shows a simplistic view of a cooling diagram, cooling age diagram. This shows the age and temperature of rotation-powered pulsars with bright enough thermal emission. And we can see that they pretty much follow the standard picture. However, when we add the other sources, the X-ray emitting neutron stars, we see straight away the magnetars, and in a smaller scale, the Magnificent 7 are just too hot to be explained by standard cooling. And also CCOs, we also see these saw these during this conference, they seem to require a light element, the presence of a light element accreted envelope or envelope to explain their higher temperatures for their kiloyear ages. So it's clear that it's actually because we know the magnetars in particular and the M7 exist, and that's from X-rays, that we are beginning to understand the important role of magnetic field decay at producing hot and long spin period neutron stars. And also the observation of CCOs, and here I just put a few references. In the past years, this has really pushed ahead a different outcome of neutron star evolution, where we believe that these neutron stars are young, but recovering from an early episode of fallback accretion after the supernova event, which is responsible for hiding their magnetic field deep into the crust. So that would explain the anti-magnetar behavior. There's the fact that they are not detected as radio pulsars, but also that the cooling rate may be affected. This could explain why evolved CCOs are not on this part of the diagram, but should, at some point after the field diffuses back to the surface, be found among the rest of the population. So it's clear it's the magnetic field that governs the neutron star phenomenology. In particular, its strength at birth, whether it decays or grows during the neutron star lifetime, and the effects that these have on the neutron star rotational and thermal evolution. And in particular, how the neutron star will be detected by us, the neutron star visibility across the electromagnetic spectrum. It's important to stress here that those channels, those evolutionary channels, are not probed by the bulk of the population, the radio pulsar population. And also they are not predicted by theory. Despite the big progress that was done in recent years, it's also important to stress that even the state-of-the-art models of field decay are built over uncertain assumptions concerning, for instance, the initial field configuration and also the level of impurity of the crust. This completely determines how much energy will be deposited in the crust and the cooling curve of the different neutron stars. And what's crucial is that, as it is, the observed population of pulsars, including radio and X-ray objects, is not sufficient to constrain those models of field decay. This is shown by the work of Goulon and collaborators a few years ago. Likewise, the phenomenology of CCOs has triggered a lively debate over their formation and fate. And however, we do not know the fraction of neutron stars in our galaxy that do undergo such an episode. And also, can we ever hope to constrain the time scale of field reemergency? We detected the descendants of CCOs later on among the rest of the population. This is determined by the amount of matter that can be accreted on the neutron star. And there are many conditions that can prevent this to happen. I just mentioned, for instance, deviations from spherical symmetry, neutrino-driven explosions and convection in accreted envelope, as well as this neutron star spin period or even the spatial motion. So this is not known from theory what can really prevent fallback accretion to occur, and also the level of field submergency. So the question is, are those alternative scenarios rather ordinary? And if not, what are the consequences to the birth rate of neutron stars in our galaxy? And of course, we also want to be able to explain within this unified picture this transitional behavior between different objects, different classes of neutron stars. So Okay, this grand unification of neutron stars is really waiting for us to know more about X-ray emitting neutron stars. They are not detected in the radio and gamma rays. So progress will only be achieved when we can extend our knowledge towards fainter fluxes. So we only know so far the X-ray bright end of the neutron star population, either from the rosettes, the very nearby ones, or when they go through outbursts. So we do need to obtain a better sampling, discover and then characterize the evolutionary state of those individual sources in order to evaluate the impact of these alternative scenarios on its neutron star evolution and detectability. So that's where we hope that eROSITA can step in. eROSITA is the next all-sky X-ray survey mission that will be launched hopefully next year in September. It's a Russian-German collaboration, and it will scan the all-sky 8 times in 4 years with unprecedented sensitivity, angular energy resolution. It will detect millions of X-ray sources, and these will require, identification campaigns will require a very crucial synergy with large-scale multi-wavelength photometric and spectroscopic surveys and facilities. But we believe that eROSITA has the unique potential for the next decades to come to really unveil the faint end of the neutron star population and hopefully help us to understand the population as a whole. So in order to create a forecast for eROSITA, we developed a model, population synthesis model, where neutron stars are born from progenitors distributed on in the spiral arms of the galaxy. After the supernova explosion, the neutron star evolves in the galactic potential while cooling down, emitting soft X-rays. So it's very important to also model the absorption from the interstellar medium. We take this into account. And also the survey properties in order to compute the number of neutron stars that would be detected above a certain limit. And then we compute Monte Carlo simulations of this model to obtain average properties. Here on this plot, I show the eROSITA effective area for 2 different configurations of optical blocking filters, which is still not decided. In comparison with XMM Newton PN, I hope you can see here, and Rosat PSPC. And here is the eROSITA sky exposure after 4 years of the survey, which is very concentrated along the ecliptic poles. So our simulations give a number of up to 100 neutron stars to be detected through the thermal emission after 4 years of all-sky survey. Their distances are within 400 parsecs and 8 kiloparsecs, with a median of 2 kiloparsecs. Their exposures are within 1.6 kiloseconds and 8 kiloseconds, and the faintest neutron stars in our detected sample are of the order of 10 to the minus 14 ergs per second per centimeter square. That means that eROSITA will be 50 times more sensitive to neutron stars than Rosat BSC, the Bright Star catalog, was. And around 30% of the sources will be brighter than 10 to the minus 13. Here I show the log N log S curves from our simulations for these 2 different configurations of optical filters. Now, to dig these neutron stars from the millions of X-ray sources that will be detected by eROSITA is not going to be an easy task. We will rely on heavy cross-correlation and cuts in X-ray color space, visual screening, and optical and infrared follow-up. And here, to illustrate, I just show our past work with the 2XMMP catalog of sources, where from our original sample of flux-limited sources of 72,000 sources, we selected 30 good neutron star candidates for follow-up. This eventually led to the discovery of one neutron star with a purely thermo-emitting neutron star in the Carina Nebula, which we have been studying ever since. Here's our expectations for follow-up. So with our simulations, we can compute the limiting magnitude that will be required for each neutron star in our sample so that we can rule out AGN and CVs in particular. So this will be based on X-ray to optical flux ratios and requiring a minimum flux ratio of over 1,000. The median magnitude required for identifications is of the order 27.4. So that means that the sources at intermediate flux can be already follow up in the immediate aftermath of the survey using current facilities. So here's already the summary and outlook of my talk. We expect of the order 100 of neutron stars to be detected in the Rosetta Sky survey, which will be of the order of 50 times more sensitive than Rosat was. The sources at intermediate flux can be followed up with 4-meter and 8-meter class telescopes in order to rule out AGNs and CVs. XMM Newton, as well as Rosetta during its pointed phase, which will follow the survey phase, the 4 years of survey, will be required to search for pulsations and eventually spectral lines, understand the energy emission of these neutron stars. Chandra will be equally important for sub-arc-second precision to search for diffuse emission and pulsar in nebula, for instance. And of course, we need to also search for counterparts in the radio and gamma ray domain. These all require to really tackling the evolutionary state of these neutron stars in the hope of then evaluate the impact of these alternative evolutionary scenarios on cooling. And of course, we expect in the long term that the next generation of optical telescope, the extreme large telescope, SST, Athena, and SCA, will help us to identify even the faintest neutron stars in our Rosetta sky. Here, leave you with the slide from Bob Rutledge 6 years ago in the first Rosetta International Conference, which, although some scaling maybe is needed on these numbers, conveys the very, very important message that we still have many neutron stars to discover in our galaxy. So, thank you.
Questions? Bettina.
I was wondering, looking at the response of the Rosetta, it seems to be more sensitive towards higher energies in contrast to Rosat. So I would think that you probably are likely to detect more hotter neutron stars than, say, the Magnificent Seven. Did you look into that?
Yes, of course, that makes sense. But it actually is more sensitive at the energy band where we expect to find the most distant ones, the fainter ones. So those will be exactly on this energy band. So, of course, for the nearby ones, there is a bit of a sensitivity factor that is lost when we compute the numbers for the whole population. The ones that we want to detect, the ones beyond the solar vicinity, are the ones that Rosetta really can make a difference in respect to Rosat.
So we will likely find similar sources like the
as well, of course, okay. Yes.
I have a question as far as we have this picture. So just 2 telescopes out of 7 will have soft sensitivity. Is it true?
It's a bit complicated. There are 2 detectors that have built-in chips, and this means that they can be operated with or without external filters. So in my simulations, I consider two different configurations, which means when they are all the 7 with external fields, which is the more conservative scenario, or when they are open, those two.
Okay, and this uncertainty, 85, 95,
Yes.
it's mostly related to this fact, or?
Yes, on the number, yes. If you look at the properties of the detected neutron stars, the very not significant difference between the two samples with two different optical blocking filters.
Okay, other very urgent questions? Then let's thank the speaker and all speakers of the session and enjoy your coffee and tea.
session. Okay, let's get started. Welcome back to the second morning session for today on multi-wavelength manifestations with the first invited talk by Andrea De Luca on CCOs and the slow magnetar in RCW 103.
I thank the organizer for inviting me to this wonderful meeting. Before starting my talk, I would like to spend 2 words to remember Giovanni Bignami. He was a dear friend and collaborator, and it's needless to say here, he was a major contributor to neutron star astronomy and to science in general. He left us last May, and we all miss him very much. So, ciao Nanni, and I will go back to the topic of my talk. In this slide, I show you the identikit of a central compact object. CCOs are soft X-ray sources sitting at the geometrical center of supernova remnants. And so, assuming that they are genetically tied to the host supernova remnant, they should be young astrophysical objects. Their spectrum is thermal and is typically well described by the sum of 2 black body curves with very small apparent emitting areas. They have no counterparts from the radio to the gamma rays. There are no associated Pulsar nebulae, nor any other kind of hints of non-thermal emission. Their emission is generally steady and unpulsed. So, what are CCOs? I will go, during my talk, looking for a template by studying different objects that have been well characterized, and several pictures are emerging for them. The first source I will be talking about turned out to be a very peculiar magnetar. This is the central source in RCW 103 supernova remnant. Interestingly, it was a sort of a prototype of central compact object. It was the first proposed radio-quiet isolated neutron star in a supernova remnant. It was discovered by Thuringer-Meyer using Einstein data, and the proposed interpretation was at odds with the evidence of long-term variability that came later in the ASCA and Rosatira. Then, in the Chandra and XMM Newton era, came the evidence for a possible periodicity. Around 6 hours was the period. It was apparent in the first Chandra observation. It was not apparent at all in the first XMM Newton observation. But in 2005, thanks to a long observation with XMM, we could assess that the source is unambiguously periodic. And the period is around 24 kiloseconds. This is the light curve. As you can see, it has a sort of sin-like shape at that time. In this plot, I show you all the kind of time variabilities that we know from this source. In the larger panel, you see a long-term light curve. Here you can see flux measurements from Rosat, ASCA, again Rosat, ASCA, Chandra, XMM Newton. As you can see, there are strong evidences for large variations in flux, large outbursts, let's say, recurrent on the few years time scale. The inset shows the short-term periodicity at the 24 kilosecond period. As you can see, when the source is at a high flux level, the modulation is complex with multiple peaks and dips per period, while when the source is at a low flux level, the modulation is much simpler in shape, with a sort of scene-like variation. At the time of the discovery of the periodicity, we had the opportunity to perform a very deep observation with the VLT, and we could not identify any viable candidate counterpart in the near infrared. Our upper limits ruled out the possibility to have a star larger than an M6 dwarf as a companion to the source. And thus, putting all the things together, recurrent outbursts, the long periodicity, the young age, the lack of a counterpart in the near infrared, we had to face a sort of unique phenomenology which called for very unusual explanations. And so different interpretations appeared in the literature, ranging from an isolated magnetar, possibly braked to 24 kilosecond rotation period by interaction with the Fallback disk, to binary systems involving very small stars, or indeed a magnetar together with a small star. Since that time, we have been monitoring the source with SWIFT, and this is a long-term light curve spanning more than 16 years, and showing the decay from the outburst occurred in 2000. The evolution can be described as a cooling and shrinking of two hot spots, and the overall energy is about 10 to the 33 ergs. Using SWIFT data spanning several years, Paolo Esposito had produced a phase-coherent timing solution which allowed us to put some constraint on the evolution of the period to, let's say, 2 times 10 to the minus 9 seconds per second. Then we have been continuing the monitoring. We were not anymore excited in the last years since the source was persisting in its very low level, but eventually last year the source reactivated. On June 22, the Burst-Haller telescope on board SWIFT was triggered by a short flare of hard X-rays coming from a direction that was consistent with the position of the CCO. This is the error circle for the origin of the hard X-ray burst. This is the light curve. As you can see, the duration is very short, around 8 milliseconds. The spectrum is thermal, and the luminosity at peak is around a few times 10 to the 39 ergs per second. As you can see in the upper figures, the image of the supernova remnant is telling us that the central source became much brighter after the emission of this kind of flare. Indeed, our last observation with SWIFT was performed by chance 20 minutes before detection of the flare, and at that time the flux, the persistent flux of the source was a factor 70 higher than in the quiescent level. We performed target of opportunity observations with Chandra and Dunstar, and we observed for the first time a hard component at with a power law shape which extended up to 30 kV. I will show you this is pulsed, and the thermal component, which is beautifully seen, turned out to be much harder than in the quiescent level. Monitoring the decay from the second outburst with SWIFT allowed us to assess the properties of this episode. This is very similar to the previous one with a slightly smaller overall energy. And here you can see the evolution of the modulation along the 24 kilosecond periodicity. This is the source as seen in quiescent with the scene-like modulation. And this is after this outburst of last year. The pulse shape changed to a more complex shape with 2 peaks per period. This is seen both in Chandra and in Nustar. So there is almost the same shape in the soft X-ray and in slightly harder range. Very recently, we performed a second observation with Nustar a few weeks ago. And the light curve changed again to the sinusoidal shape. So it seems the source is relaxing. And here you can see our hard attempt to put all light curves in phase. This is a tricky task since the light curve is changed very much in shape. And so, as an attempt, we started from the solution we obtained in 2011 using SWIFT data, and we extended it using data in the quiescent state, so Chandra data showing the sinusoidal modulation. And then we extrapolated it after the outburst and before the first outburst. And as you can see, the second outburst involved, as I said, a change in the light shape, in shape of the light curve. And interestingly, the sinusoidal shape, which is seen in the most recent Nustar observation, is not anymore aligned in phase with the sinusoidal modulation of the quiescent level. It seems within errors, let's say, that there is sort of a 180 shift in phase, as if the outburst switched on an emission area, an emitting area which is on the opposite side of the star. A very likely counterpart was discovered in the near-infrared. It was published by Tendulkar and collaborators. It was discovered in the H-band with HST soon after the 2016 outburst. Very faint, AB magnitude in the H-band 24. And it was not seen in the previous observation with HST with NICMOS. The same source is seen in our images taken with the VLT. This one is not apparent at the same position in all their images. This is a KS band. It's not easy to assess colors of the source because of difficulties in comparing fluxes measured with different instruments on a crowded field, varying observing conditions, uncertainties in the reddening. But in any case, it seems that the properties of the source are broadly consistent with the one of, let's say, typical counterparts of magnetar in outbursts, with ratio of the infrared to X-ray luminosity around 10 to the minus 5. So, all of the aspects of the phenomenology of the source can be fit rather easily within a magnetar scenario. The millisecond hard X-ray flare and its spectrum, the large outburst in persistent emission, the changing spectral shape with the appearance of the hard power law, the changes in pulse shape and pulse fraction, the overall energetics of the outburst, the faint interference counterpart. Of course, what is not easy to understand is the period of 24 kiloseconds. It's hard to believe that this was a magnetar born with that period, and so we need for a mechanism to slow down the rotation of a neutron star to that super slow rate in, let's say, a few thousand years. And it seems that a more promising picture is that involving propeller interaction with the fallback disk. Even if there is a recent investigation by Rosgold Baperna and collaborators which argued that it's quite difficult to believe that large disks survive around active magnetars, there are recent papers, for example, the one by Hoy Anderson, which show that a very small amount of matter could be enough to break down as needed a neutron star in the right time scale, but provided the neutron star has a very large dipole field, around 5 times 10 to the 15 Gauss. Other possibilities that are worth exploring is that propeller interaction appeared in an earlier phase of fallback accretion. This was proposed by Sergei Popov and collaborators, and we also proposed it in our paper published in the Outburst. In any case, no detailed computation have been performed so far to explore this scenario. So it seems that we have a framework to interpret this source, but it seems like it is a very peculiar, possibly unique source. And so I move on to the next small sample of CCOs, still looking for an explanation of CCOs as a class. I will talk about the so-called antimagnetars. A key discovery by the Columbia Group, Jules Alpern and Eric Gotthelf, has been the detection of pulsation and the measurement of the period derivative for 3 sources of the sample. The one inside PAC-PSA, the one inside PKS 1209, and the one inside Cas79. These are 3 rather fast pulsars, 100 millisecond, 400 millisecond, 100 millisecond, and the period derivative is very small, very small. On the one side, this required a very large observational effort in order to measure this effect by means of phase-coherent timing technique. Implications of the measure are very important. First of all, the dipole field that results from the P dot is very small, 10 to the 10 to 10 to the 11 Gauss. Second implication is that the characteristic age of the sources exceeds by a huge factor the age of the host remnant. Characteristic ages of order of hundreds of million years, while the age of remnants are of the order of thousands of years. Third implication is that the X-ray luminosity of the sources cannot be in some way powered by rotation, since the spin-down luminosity is very small for all of the sources. So the framework we have to face is that these are isolated neutron stars with a weak dipole field. Their position in the PP dot diagram is here, and since CCOs and magnetars are sitting on opposite sides with respect to the bulk of the neutron star population detected as a radio pulsar, Eric Gotthelf called these objects antimagnetars. I will spend a few words to review the phenomenology of the 3 antimagnetars, since there are very interesting points that are helping us to understand their nature. The source in PKS 1209 has a spectrum which displays several absorption features superimposed to the usual double black body continuum. Those features have harmonically spaced energies, and their nature has been somehow debated in the literature, but after the measurement of the P dot, the cyclotron interpretation, cyclotron by electron, seems to be the proper one, since the expected energy of the fundamental is very close to 0.7 keV. The B field computed by the cyclotron interpretation is around 8 times 10 to the 10 Gauss, while the default field from the spin down is around 10 to the 11 Gauss. Another very peculiar point here is that the modulation we see for this object is almost entirely due to the phase modulation of the features. The continuum is not pulsating. It's pulsating at, let's say, 2 to 3% level, while the features are much more modulated at the 50 to 20% level. Going to the CCO in Papisei, these are light curves above and beyond 1 keV. As you can see, the modulation in this source is in antiphase at soft and hard energies. This is the pulsed fraction as a function of the energy. As you can see, around 1.2 keV, it goes to 0. This is a very peculiar behavior, indeed preventing detection of the modulation when using the whole data set from XMM. And it could be explained by assuming that the thermal emitting pattern is peculiar. We need the two regions with different areas and different temperatures sitting at the opposite sides of the neutron star. And the large anisotropy which is required on the surface of the neutron star, of course, it's at odds with the expectation for a weakly magnetized source. This is the spectrum. Again, it is well fit by the usual double body curve, but there is also a feature at low energy. It could be described either as an emission line or as a couple of absorption lines. Here, the cyclotron interpretation is not indeed very pointing to the correct value of the field. At least the expected cyclotron energy for the spin-down magnetic field is 0.2 keV at the equator. But in any case, this does not seem a problem in interpreting the feature as a cyclotron scattering. Another piece of evidence is that the feature is very likely variable as a function of the time. It is variable as a function of the phase, rotational phase, but also as a function of the time. It seems that the feature changed in energy and also in intensity on the time scale of, let's say, 10 years. The last antimagnetar that I'm mentioning is the one in Cas 79. Here the spectrum is featureless. Two black bodies, small emitting areas as usual, and very large pulsation, 65% pulse fraction. The spectral shape in this source does not depend on the pulse phase. And this is another peculiar aspect of the phenomenology. This can be explained by an emitting pattern with two hotspots which are collocated on the surface. The hotter one is inside the cooler area, and the rest of the surface is essentially emitting no X-rays. Slavko Bogdanov, who performed this kind of modeling, also pointed that emission should be beamed in some way to achieve a high pulse fraction. Both the peculiar surface emitting pattern and the beaming are not expected in a weakly magnetized neutron star. So I go back to the original problem. What are CCOs? And this is the list of CCOs. 13 sources, including a couple of candidate CCOs. And these are the sources that I've been describing, the RCW103 magnetar and the 3 antimagnetars. As I said, possibly the peculiar magnetar in RCW103 is a unique source. And there is the possibility that other CCOs are magnetar. Maybe yes, I will say. But for the moment, let's assume that the better template to explain CCOs as a class is provided by the 3 antimagnetars. So we can explore the possibility that the weak dipole field is the physical basis of the CCO class. In this picture, we have to face some difficulties. The first one is the peculiar thermal map. As I said, it's not easy to explain why a weakly magnetized neutron star should have very large surface temperature anisotropies. Different explanations have been proposed. Spin down power is not enough. Accretion is ruled out by timing. Possibility of localized injection of energy by magnetic field decay as in magnetars, well, we possibly should observe some variability, but indeed, in the case of SW103, we did. This seems not the better solution for steady sources as the rest of the CCOs. And so a solution is that the X-ray luminosity is powered by residual heating, by cooling of residual heat. And what we need is an isotropic transfer of the heat from the core of the neutron star, which requires, of course, a strong magnetic field in the crust. A toroidal component of the order 10 to the 14 Gauss is needed to screen heat transfer towards the equator of the star. And this should be coupled to a poloidal component at least 3 orders of magnitude smaller in intensity. This is the configuration of the field that is needed to explain the sources as weakly magnetized neutron star. Another problem with the weakly magnetized picture is that concerning origin and evolution of CCOs. As was mentioned before me by Samar and by Adriana, CCOs are frequently formed, and we can say this by simply counting how many of the sources are inside supernova remnants and comparing this number to the number of other classes of sources, radio pulsars or magnetars. They could be more frequently formed than magnetars. Their magnetic field is weak, and if it is constant, we would expect to have a sort of overdensity of sources in the region surrounding the 3 antimagnetars, supposing that at least some of them emit in the radio band. But we do not. This is an underpopulated region. And the related issue is that if one uses the birth rate estimates for different classes of neutron star and compare them to the overall collapse supernova rate, well, the two numbers do not agree, and we have too many neutron stars. And so this was an argument put by Keane and Kramer, suggesting that evolutionary links are needed in order to solve this issue. Which are the frameworks for a weakly magnetized neutron star? Halpern and Gottlieb suggested that CCOs could be weakly magnetized at birth because of an inefficient dynamo mechanism in a slowly rotating protoneutron star. But it seems not appealing since CCOs are not that slowly rotating, and this does not help to solve other issues in the phenomenology. Another possibility is that we are facing with sort of quiescent magnetars with a very, very weak dipole field. There is the argument of variability. A third possibility, which has already been discussed before me by Samar and Adriana, is that there is an important role in from fallback accretion. This is the so-called hidden magnetic field scenario. Prompt accretion of fallback material could bury the magnetic field and confine it in the crust of the neutron star, and the magnetic field could then re-emerge by diffusion on a time scale that would depend on the amount of the accreted matter. And there are several works that explore the possibility, and they point out that around 10 to the minus 3 solar masses of accreted material could be enough to screen strong fields, and that the time scale for emergence could be in the range of 1,000 to tens of thousands of years. This would imply that central compact objects, if are born with this mechanism, could turn later in normal pulsars or even in high magnetic field pulsars or magnetars. And this would solve possibly the birth rate problem. It is a scenario which is very difficult to be tested using timing, at least in the X-rays, since it would be needed to measure the breaking index for the sources, which have a very small spin-down rate, and so it is very hard as an exercise. There is some supporting evidence for this scenario, observationally, from radio pulsar timing, the small breaking index for a few very young pulsar have been interpreted as an evidence for a growing magnetic field, and there is some further support in the absence of evidence of weakly magnetized neutron star in high mass X-ray binaries. But in that case, we must say that there is a large fraction of sources for which we have no information about the magnetic field. The hidden magnetic field scenario triggered searches for descendants of CCOs in other classes of neutron stars. And so there were searches using Chandra XMM for anomalously high temperature in mildly recycled pulsar, or in seemingly old pulsars positional coincidence with supernova remnants, or in weak field pulsars, let's say pulsars that sit in a region close to the CCO ones, but no one was found. Searches are still ongoing for CCO descendants among seemingly older pulsars with larger magnetic fields. A possibility that we could consider is that possibly the timescale for reactivation of the pulsar mechanism is larger than expected, or that CCO descendants are indeed radio quiet. And there is a peculiar source dubbed Calvera. It was discovered and proposed to be an addition to the Magnificent 7 X-ray dim isolated neutron stars. Later, it turned out to be a sort of peculiar rotation-powered pulsar with a high spin-down luminosity, around several times 10 to the 35 ergs per second. But it is not seen neither in radio nor in the gamma rays. It only emits thermal-like X-rays. And so it was proposed to be an evolved CCO. But indeed, the age and the distance of this source are almost totally unconstrained. It is at very high galactic latitude. And so it's not possible to conclude that this is a descendant of a CCO. It is radio quiet in any case. So I came to my conclusion. The sample of CCOs that were initially a disappointing sample of boring sources is proving to include very interesting sources, and their interpretation is providing hints in order to go towards a unified theory linking different classes of neutron stars. This theory should give an important role to fallback accretion and to the interaction of the neutron star with the fallback material in a range of different regimes and with different magnetic field configuration, of course. This is a scenario that has many parameters, and it will be difficult to constrain it using observations, but indeed, on the observational point of view, there is a lot of work that can be done with existing facilities and with future observatories. For instance, we have to monitor CCO pulsars to see deviations from their steady spin down. We can search for pulsations in the large majority of CCO sources, which have not very constraining upper limits in this. We have to search for long-term X-ray variability, which could unveil that a few of them are magnetar. Indeed, the possibility that a few of them are quiescent magnetar cannot be ruled out on the basis of simple spectroscopy. Are they radio quiet or simply radio faint? We do not indeed know, and possibly with future observatories it will be possible to assess this issue. We have to continue searching about possibility for their descendants and for new members, for instance with the Rosita, as Adriana said. And clues to the evolution can come also from timing radio pulsars and other classes of neutron stars. There is a lot that still need to be done regarding specific sources, and we have lots of data for the three antimagnetars, and possibly for them it could be possible to perform some sort of very detailed modeling and to infer the magnetic field topology, which could be an important ingredient in order to understand their nature. Okay, I stop here. Thank you.
Thank you very much for this excellent review. We have time for a few questions. Oleg?
For RCW103 source, was there any evidence of spectral features in any observations in any states?
Well,
have you checked?
Yes, I did not mention that we have a deep observation performed with examine Newton after the second outburst. And of course, we had a look in this data. And, well, to be frank, if you look at the plot that you can obtain by making the histogram of energy versus phase of collected photons, well, you would like to see a feature there. But it's not easy at all to constrain these using phase-resolved spectroscopy. So, yes, I would like to believe there is a feature, but possibly we cannot say that there is as a unique explanation for the evolution of the spectrum as a function of the phase.
Any, Ali?
Thank you for the very interesting talk. I want to make a comment about fallback. Now, fallback accretion is coming in, it's suggested that in various connections. I want to point out that the assumption that it's spherical to bury the field and for the field to come back has a number of problems. First of all, the statistics and the connection with the supernova rates already suggests that there are evolutionary connections between these classes, and then to assume that every case where you employ fallback is actually spherical, which should be rather unusual in a supernova, compounds the problem of the statistics. And secondly, if you allow for the fallback to carry some angular momentum, then it would remain in a disk and it would regulate the evolution for an extended period of time, and it would explain the period regularities. And in the presence of a fallback disk, the torque on the neutron star is not a dipole torque. And you can easily explain the seemingly anomalous breaking indices with a fallback disk scenario that's consistent with explaining the period and the period derivative and the second derivative and luminosity. All of that said, I think the reason the CCOs are very interesting, in particular RCW103, is it's so exceptional and way out from the regularity in periods of all the AXPs and SGRs and the dim isolated stars that it really is going to be, I think, very important. My colleague Ünal Ertan has the codes with fallback disks which he can successfully apply to the dim isolated neutron stars, AXPs, SGRs, but so far not in detail to the source in RCW103. So that's really a challenge. Thank you.
Any other questions? Yeah, go ahead.
What is the multi-level spectrum for the 6-hour period, including optical and X-rays?
Yes.
Where is the KTS?
As I said, we have a detection of this source in the KS and H band, but these are from different instruments, different epochs, and it's not easy to say which is the difference in flux between the two near-infrared bands. So it's not possible to say if it's brighter in the KS or in the H band intrinsically after the reddening. In any case, what seems to be a conclusion is that the flux in the near-infrared is around 10 to the minus 5 times the flux in the soft X-rays. And so this kind of ratio is the one that is observed for several other magnetar candidates when they are in active state. So this is the only strong conclusion, let's say, if this is a conclusion that we can have from this data. It's not possible indeed to talk about colors of this source.
Okay, one very last question from George.
It is actually a continuation of Yura's question. If do you understand right that if you plot X-ray spectrum and those 1 or 2 points in near infrared, flux densities, yes, and connect them with a power law, what would be the slope?
I didn't try. I admit I didn't try to connect them with the power law you see in the X-rays with Neutron.
Okay.
So we can check.
Okay, lots of interesting questions. I had a burning one, but I'll postpone my question for later. So we have to move. Thank you very much again, Andrea. So our next speaker is Bettina Posselt, who's going to be talking about magnificent in the infrared and another unusual isolated neutron star.
All right, it's a pleasure to talk about a particularly magnificent member of the Magnificent Seven, and I also want to acknowledge my collaborators who contributed to some part or another of this more long-term project. All right, so I will start with giving you some background, very quickly summarizing some properties of the Magnificent Seven, and also with respect to this source, which is RSG 0806, I want to quickly also mention previous Herschel observations. And then I will come to linear infrared observations and the constraints we get from that, and discuss potential interpretations. So just as a reminder, when we look in the PP dot diagram, so the Magnificent Seven are located between the rotation-powered pulsars and the magnetars, and this places them in a very nice spot to study neutron star evolution models. And here is a quick summary of the main properties of the Magnificent Seven. And I don't want to go into too much detail of that. What I want to point out is that they have only thermal emission in X-rays, so there's no detected non-thermal emission there. And they are hotter than they ought to be, so Adriana already pointed this out. So the the X-ray luminosity is much more than you could get from spin down, for example. Another important fact to mention is that they are radio quiet and that they don't have any detected pulsar with nebula, neither in the radio nor in X-rays. So with respect to the mentioned neutron star evolution, it is important to keep in mind that there's more than one model. So the most commonly preferred model is that of the magnetothermal evolution, and we have already heard a little bit about that you have decaying magnetic fields which provide extra energy either to heat the source or to also create these huge bursts we see from the magnetar. So this can nicely explain these effects. One prediction this model does is that you would expect that high magnetic field pulsars should be hotter. And this was studied by the group of Vicky Caspi and her postdocs. And of the 5 high B pulsars they investigated, only 2 turned out to have these high temperatures. So this may indicate that there is still some work to do to fully kind of confirm this model. And maybe there are extra contributions you need to consider. And one of these could be the fallback scenario, which could be also maybe even an alternative scenario. And in this scenario, you have this a fallback material forming a disk and applying a torque to the neutron star. So basically, the magnetars only pretend to have a large magnetic dipole field. And the different disk masses would explain different neutron stars. However, you need a multipolar magnetic field set up to explain these bursts, these huge bursts of magnetars. For this model, if you observationally want to test it, the problem is that we currently only have one detected fallback disk. And this is a Spitzer detected fallback disk, or a Spitzer detected disk around the magnetar 4U0142. So for me, this was one reason to look at the Magnificent Seven, since they are closer and they are supposed to also have a remnant fallback disk, and to probe for these disks with Herschel and Spitzer. And we found 2 potential candidates. One of those is 0806. And here are some quick properties of that isolated neutron star. So it's one of these Magnificent Seven, which are also sometimes called X-ray dim neutron stars or exothermal isolated neutron stars. And what I want to emphasize here is that it is a very low distance in comparison to, say, magnetars. So it's about 250 parsec. And with recent Chandra observations, we constrain the proper motion if we use a very conservative phi sigma limit to less than 50 milliarc seconds per year. This is a project I'm doing with Christian March and Adriana Pires. And here is a quick view of the Herschel image. So it's a very clear detection. So it's a 10 sigma detection. What is less clear is whether this is related to the neutron star or not. So at 70 micrometer, we don't detect it, and in Spitzer, it's less, it's not conclusive. In the left corner, you have the Herschel image. The big image is the Hubble observation by Kaplan et al. And on the right, you have the UV, and on the left, you have the optical image, which shows you that the region around the neutron star is pretty empty. It also, the magnitudes which I quote here also indicate that this is a really faint object in the optical. So I don't have time to go into this interpretation of the Herschel observations, but at 160 micrometer, what you think you detect usually with Herschel is called dust. And if you assume for the moment that this dust is associated to the neutron star, it would imply a large dust torus at a relatively large distance from 150 AU multiplied with the size of the grain, square root of it. However, an alternative interpretation could be also an ISM clump, and in particular for the direction of 0806, this is indeed, I think it has a probability of 20% to be an ISM clump. So now here's the near-infrared observations we had until recently. So the Herschel observation motivated us to go back. Yes. Okay. Right. Can you still hear me? All right. So the Herschel observation motivated us to go back to the source, which we had observed in near-infrared to look for substellar companions. And at the time, we found with the VLT a very low significance and flux enhancement in the H-band, which we didn't fully believe. But going back, we observed it also with Gemini in the J-band, and now got another insignificant flux enhancement. But taking together these two different instruments, different telescopes even, different bands, you get a combined significance of 3 sigma. So this at least gave us enough arguments to propose for Hubble. I also show here the Spitzer image, and there is a slight flux enhancement, and I give here the formal flux measurement. However, I don't use it really because for Spitzer you really deal with source confusion from neighbor sources, and it's very uncertain. So this on the left side here is the Hubble image, so a part of the Hubble image, and a zoom in. And when you measure the flux and plot it in an SED with nu and nu times the f nu, then this point falls here. This is the Gemini point, and they both have 1 sigma errors, but for Gemini it's huge. And here's the UV and the optical. So you can see that the Hubble magnitude has a pretty low error, so it's detected with a high significance. While, as I said, for Gemini, this is much less certain. The interesting thing with this near-infrared source is that it is extended. And you can probe for this by subtracting the point spread function. This sounds easier than it is with Hubble because based on the data reduction procedure, the pixel phases are related. So you need to do some extra tricks to do that. And so we use this bundle software by J. Anderson. And I did the point spread function subtraction for the target as well as for comparison sources. And here we have a comparison source of similar magnitude. And you can see it's clearly subtracted, nicely subtracted, but for the target, there is flux remaining. And I get the similar results for other comparison sources, faint ones, but also brighter ones. So I'm pretty confident that there is indeed extended emission around the source. Probably the extension is about 0.4 arc seconds, which translates to about 100 AU at 250 parsec. However, one should not forget that even Hubble has a certain width of, the point spread function has a certain width. So in this band, it's 0.15 arc seconds, so this will blur your image a little bit. So of course now the question arises, what is this? So first thing which comes to mind is, of course, could it be just a by chance background object? Other possibilities are Pulsar wind nebula, or maybe some interaction with an ISM clump, or it could be gas or dust emission from a nearby structure like a disk or torus. One should also not forget that you could still have contributions, say, from the neutron star or from the substellar companion. And I will first discuss the background object, then quickly mention these contributions, and in the end talk about these actual interpretations of the extended emission. So regarding the background object, So here you have on the left you have the Hubble image, on the right the previous VLT image, and just with some positions overplotted. So you can take the whole Hubble image and get a source density, and this, together with the separation of your source from other other constraints on the Neutron star position and their uncertainties, gives you a certain probability. So if you use Chandra and this conservative proper motion limit I mentioned before, then you arrive at, by chance, background probability for a background source of 8%. For HST, I took a very conservative positional uncertainty of 0.1. So this refers to the old optical image, which is, of course, much better. The position is much better constrained than in Chandra. And this, here the proper motion uncertainty basically governs the total uncertainty. And here you arrive at a probability at 4%. So overall, I think the chance that it's by chance background object is really very low. In particular, since these are very conservative estimates, I think I can even get these further down. So regarding the contributions, if we look at the SED, and we just concentrate now here on this part, if you see how the UV and the optical connect, right? So the contribution from the neutron star is really negligible, either from thermal emission or the magnetospheric emission. You would not expect that it can produce this type of excess. For a substellar companion, this may be different. And I remind you that, as I said, 20% of the flux could, in principle, come from a point source. And if you do certain assumptions regarding the age and the cooling curves of substellar companions and so on, then you can estimate that the H-band measurement would correspond to roughly 1 Jupiter mass. So usually you would use colors to say something, whether it's a substellar companion or not. But right now, our uncertainties, especially in the J-band, are highly uncertain. So it's without use for this. And I don't want to say there is a substellar companion. It's just something one should keep in mind, that this could be a contribution, but it's maybe asking for too much to have extension and a substellar companion. Okay, so coming to these interpretations. So one interpretation could be a pulsar wind nebula. And we will hear a lot about this later on in the next sessions. So I only want to mention that in principle, you can have close to the neutron star anisotropic wind structures, and more, if you assume an isotropic wind structure, then you can kind of get these Bow-Shock features. The problem here is that you need relativistic particles. So you need these accelerated particles creating these shocks and so on, which we see then in mostly in X-rays. And the question is, where should these particles come from? So these Magnificent Seven do not show strong signatures of magnetospheric emission. And they have no radio emission, they have no non-thermal X-ray emission. The only thing which is basically remaining from magnetospheric emission is the optical. And as George already pointed out, some of these objects deviate strongly from a Rayleigh-Jeans tail. However, 0806 is not one of these sources, so the deviation is rather small, and in principle it's still consistent with a Rayleigh-Jeans tail. Moreover, it has been investigated by Kaplan et al. When they analyzed all these papers, all these observations for the Magnificent Seven, whether atmospheric effects or So what I wanted to say is that Kaplan et al. Already investigated whether magnetospheric emission could explain the optical deviations, and they came to the conclusion that for several reasons, mostly you would need huge luminosities for the non-thermal emission, that it's unlikely. So in principle, there is still this possibility that there might be some magnetospheric emission hidden. But I think overall, Pulsar Nebula appears currently a bit unlikely. So I leave it here with a question mark to account for this slight deviation from Lorentz tail. So what remains is that the emission comes close from the vicinity of the neutron star. And of course, now the question is, does it come from interaction with the ISM, or does it come from, say, a surrounding structure? And related to the question, particularly if you want to know whether it's coming from the ISM, is whether you deal with gas emission or you deal with dust emission. And if we probe, say, the ISM and with gas emission, if you look in the H band, it's very unlikely that you get heated the ISM to that temperature that it emits in, thermal emission in the H band. What you can get are lines. And in the H band, there are some lines of molecular hydrogen, but they are strongly forbidden. But in principle, you could excite them with UV fluorescence or collision in shocks, which on first glance sounds pretty promising. However, from studying the regions where these lines occur, like in young stellar objects or AGB stars, for example, for the second possibility, we know that the densities must be very high. For the first, basically what excludes it is the low NH of RxG or 806. From that, we know it is in a low density environment, and it's so, the extinction is so low that at this part there's no way that the molecular hydrogen is shielded, so it can be quickly destroyed. So you have a very low molecular fraction of molecular hydrogen. So it seems that this line emission from molecular hydrogen is very unlikely. Okay, so let's talk about dust. So you could have emission from the dust in shock fronts or via stochastic heating. The problem here is that you deal with likely small grains, and these small grains cannot be easily approximated as we did, for example, with Herschel. You are in a range, wavelength range, where this is not possible, so you need to do a full radiation transport calculation. And with one point in SED right now, this is not really promising. So what I did, and in full knowledge that this is not correct, is a crude black body estimate, so to just get an idea where these dust grains would be. So if you assume that the H-band emission is, say, the maximum, then you get this temperature of 1,900 Kelvin. And you can, assuming X-ray irradiation, get then a separation from the neutron star, which, if you assume that all the X-rays are absorbed, is at the light cylinder, roughly at the light cylinder. However, an efficiency of 1 is very unlikely, so very likely this moves even closer to the neutron star. So if you deal with real dust, then of course this will shift again backwards, more outwards. But I think the main result of this little exercise is that you can only heat very close dust. So the dust cannot be, in an ISM clump far beyond you. So you need to be really either sitting in an ISM clump or you must have dust around you to have these emission. So let's look at the ISM distribution for this source. So here is a 3D model by Lallemont et al. And I marked the position, the line of sight direction for 0806. So basically you look in this direction, this is where the source is located. And based on the NH, I had originally inferred that it must have a distance of around about 250 parsec, because it must sit before that little clump here. However, if you look at these clump structures in general, it is very unlikely that you basically have the neutron star and just behind it you have a huge wall of dust. So it seems unlikely that this can, that the dust is coming from the ISM simply because you have a very low NH of the neutron star, and it's not consistent with sitting in a clump. So the other possibility is now, of course, that you have a surrounding structure. So you could heat gas and dust by the irradiation, but also by other effects like the propeller effect or turbulence in the disk. And I want to mention here this latest work by Ünal Ertan, which Ali Alpa already mentioned in comments. So they tried to reproduce the optical excess of the Magnificent Seven, and they were successful in doing that by assuming that the magnetic torque of the far back disk heats the disk. And so here he has a minimum temperature in the disk and a maximum temperature, which can then describe the optical excess. So this is taken out of his paper, and it's particular for 0806. And the model was done for an inclination of 60 degrees and an irradiation efficiency of 10 to minus 5. So our H-band measurement falls where this little star is, so it's above the prediction. However, if you adapt the disk parameters and the inclination, it is very likely then that you can get it to the point which is needed. The problem which may be there is that the disk surface needs to be warm up to this large extension we inferred, which is on the order of 10 to 15 centimeters. And so this may be possible, but right now it's not completely clear. And to summarize the current constraints, so there is for sure a detected, extended near-infrared source at the position of RxD 0806. And it is very likely associated to the neutron star, but none of the interpretations right now, the Pulsar Nebula, the irradiated ISM clump, or the disk torus, are 100% convincing yet. To me, the disk interpretation looks a little bit more promising than the other ones, but even that model has some problems. So the main issue we are dealing with is that we just have this one point, so we need definitely more constraints in the SED to get the spectral slope and determine, do we deal with thermal emission, do we deal with synchrotron emission, do we have lines? And so this will be the next steps, and one step is that we now got K-band observations and hope that this will, provide a little bit more clue on the slope of this near-infrared source. Thank you.
Okay. Thank you very much for this very thorough study. Questions? Ali?
Thank you, Bettina. This is really, I think, fascinating. My question is, to take this extended source at 0.4 arc seconds, you subtracted the point spread function, but the size of the point spread function is itself 1 arc second.
No? 0.15.
0.15.
0.15.
Okay. So does that mean that anything closer to the neutron star than 0.15 could still be there and not resolved as an extended source in this? Because 0.15 at that distance is still sizable.
So first of all, the flux, and so what I showed is for including this point source contribution. So I did the subtraction only to demonstrate that it is extended. That's all what I did. So all the estimates I have include the whole source. And it is definitely possible that there is something very close. It's just not resolved.
Yeah.
So even Hubble can, at the moment, not resolve it. JWST may be able to resolve. So in principle, we could see a ring, and we would not notice it right now. So you would see that maybe with JWST.
Okay. Other questions? I'll ask. Have a question on you mentioned there was an absorption line in the spectrum.
Yeah, there's a broad absorption feature.
Right. So is it consistent with the B determined from PP dot?
So this is not. I believe it is. So, but I don't have the values
more or less,
mind.
yes. And so I'm wondering if there's possibly any connection to a torus for that line. What's the estimate of the mass of the torus or disk, if it is the case?
I think I haven't seen actually the mass, but I think it's a few Earth masses, right? What you usually have in the fallback disk. Yeah. So for the Herschel, I get also like something fewer,
right.
Less than an Earth mass, so really small. But this is just the dust. This is not the gas. Okay. Right? And usually you have a factor 100 in normal ISM material.
Mm-hmm.
So.
Okay. Any other questions? If not, let's thank Bettina again. And the next speaker is Alice Borghese. Phase-dependent absorption features in the X-ray spectra of X-ray dim isotope.